In 1969, Neil Armstrong and Buzz Aldrin became the first men to ever land on the moon. This, as well as many other moments in the preceding decade, all helped contribute to make aerospace what it is today. Through the great achievements of these astronauts, millions of people were captivated and inspired to follow in their footsteps and become aerospace engineers. I am one of those people. Hello, I am Andrew Nakos, and I am studying aerospace engineering. These are just a few things about me. I'm a junior at Frisco High School. I play lacrosse and indoor soccer. And this year in ISM, I'm studying aerospace engineering. Just a little bit about aerospace engineering. It is the study of aircraft, spacecraft, and satellites, and how they all interact with the atmosphere and other things so that you can make sure that these things fly. My quote for this year is, "Ships are safe in their harbor, but that's not what ships are for." One big reason why I signed up for ISM is so that I can get out of my comfort zone and do things that I never would have thought I've done before. And so far this year, that's been a reality because I have a great idea for a final product. I've had 5 interviews and a mentor for this year, which I wouldn't have imagined doing until I did internships in college. Alright, now I'm going to talk to you about the 5 interviews that I conducted earlier this semester. My first interview was with Mr. Dustin Miles, who's a senior materials engineer at Lockheed Martin. He works with the financials of the company, since he's not exactly an aerospace engineer, and his previous experience in business gives him extra credibility. And this business that he did was actually a candy company that he ran in his elementary school all the way through high school, and he earned $50 profit a week, which is pretty good for a little 10-year-old. And so one big thing that he talked about is the financial viability of the company. The structure of the company, the assets and liabilities are things that are important to the company, and the importance of the financial success of the company is because companies are all about making money. If money didn't exist, then most likely neither would companies. So because of this financial success, Lockheed Martin spends about $1 billion in labor every year. They have over 10,000 employees, which includes those directly employed by Lockheed Martin and contractors. And one F-35, which is the main product that Lockheed Martin works on, since they have a contract with the U.S. Department of Defense, takes 2 years to produce and costs on average around $125 million. He also stated the importance of college. Receiving a good education is very important, and so he graduated from the business school in Texas because of his experience in business in the past. 3 colleges that I'm looking at for aerospace specifically are Texas A&M, Georgia Tech, and Colorado Boulder, all of which are rated in the top 10 in the nation for aerospace engineering. My second interview was Mr. Bob Thornton, who is now currently my mentor. He's the flight test engineer at Bell Helicopter and works with experimental aircraft. The most recent project he's been working on is the 525 for Bell. And he values resourcefulness and the design process, which I'll explain shortly. The design process goes from design to construction to testing. These 3 things are the key concepts of aerospace engineering, because you have to design your products from brainstorming to conceptualization to construction, which is actually building your product, and testing it to make sure that it works for a consumer. My third interview was with Mr. Peter Romano. He's an aerospace engineer at Bell Helicopter, and he works projects from start to finish. So he'll design the projects, oversee its production and testing, and he values hard work and education. So one thing that he explained to me was a design phase. And in the brainstorming phase, people come up with a concept to fix a problem. So for example, this is an example of a brainstorm. Like, if you wanted to make an aircraft that's the best at getting something from point A to point B, you have to decide whether it's an airplane, a helicopter, or a drone that'll do the job best, depending on what costs the cheapest, what's most efficient, and reliable. The second part, the design phase, is the actual design, where employees make blueprints and they test it in computer simulations to make sure that it all works. So this is an example of a blueprint for an F-35. And they also make 3D models from these blueprints in a CAD program where they can simulate the test. My fourth interview was with Mr. Jeffrey DeHoe from Lockheed Martin. He's a senior materials engineer, and he works the layout of the factory floor. And he says that all expenses in production is lost money because you don't get paid to produce an aircraft, you just get paid for the final product. So the main thing that he does is designing the factory floor, and two key things that he looks for are the flow and the ease of access. The flow is important because it reduces the travel time between places, so you can get an aircraft built more effectively and efficiently. For ease of access, the employees need to be able to effectively work in their workstations so that they can get the project done as quickly as possible. And companies have used this assembly line structure since the start of the Industrial Revolution because it's undisputably the most efficient way to produce something. So this is just a picture of the factory floor from when I was on a tour with him of the factory, which is his main workplace at Lockheed Martin. And this is the final assembly line in which all the parts come together so that they can put the aircraft together, and it looks pretty cool. These are just some locations of contractors and subcontractors for Lockheed Martin around the world. Our location, Dallas, is highlighted. My fifth interview was with Mr. Lee Cross, who unfortunately did not have a picture of himself on LinkedIn. He's also a flight test engineer at Bell Helicopter and works with experimental aircraft such as the 525 that Mr. Thornton works on, and they actually know each other. He values experience very highly in the workplace. And so what they do is the flight test phase, which is the third and final phase of the design process. And if it fails in the flight test phase, then you have to start all over the process to make sure that your product will work. And this is just a video of a rather unsuccessful flight test.
On June 28th, NASA's Low-Density Supersonic Accelerator Project conducted the first shakeout flight of a new way of testing technologies that will one day be used to land heavier, more massive payloads on the surface of Mars. We used a large 34 million cubic foot scientific balloon to hoist a 7,000-pound test vehicle to an altitude of 120,000 feet. The test vehicle was then released from the balloon, spun up for stability, and a large solid rocket motor accelerated to 4 times the speed of sound and an altitude of 180,000 feet, a condition very similar to conditions we see at Mars. Once we reached the correct speed and altitude, we despun the vehicle. And then we got a chance to test our new supersonic inflatable accelerator. Camera lens covers deployed, we see that it inflated very uniformly without disturbing the vehicle too much. And now we're seeing previously unreleased, high-definition, high-resolution, high-speed video taken during the test. We used the supersonic inflatable accelerator to slow us to something closer to 2.5 times the speed of sound. We used a balloon to help deploy the new supersonic parachute. The balloon is shot out the back of the vehicle at over 200 feet per second, and then we cut the balloon free and it begins to pull the parachute off the back of the vehicle. As the parachute begins to inflate, we see one of the surprising aspects of this test, which is the early onset of tears in the parachute. We see where those tears began, how they propagated, and otherwise how the parachute behaved as it began trying to inflate behind this very blunt object, moving 2.5 times the speed of sound, punching a hole in the atmosphere, and creating an extremely turbulent, chaotic environment for the parachute to exist in. We now have a data set that we will use to prepare 2 more tests beginning in June of 2015.
Okay, so as you can see in that video, the tests are very scientific, very precise. Like he mentioned that the altitude of the ship had to be at precisely 180,000 feet and had to be spinning a certain direction at a certain speed so that they could reproduce these scenarios very easily and test a new design for the parachute, which they are producing now, and will test it earlier this summer. So as in all of these phases of a design process, everything must be very precise so that you can build according to parameters, you can test according to parameters, and you can ensure that your product always goes up to par. Okay, good. Thank you. All right. So after all these interviews, I decided to ask Mr. Bob Thornton, the flight test engineer from Bell Helicopter, to be my mentor. And this is because of his extensive resourcefulness and knowledge in the field, and I think he can help me with my final product greatly, which will be very difficult to build. So far, we haven't had too many mentor experiences because we did our mentor visit and then a few calls because he's out of town currently in Amarillo working on the 525. Now I'm going to move on to the research I've done so far this year. So the first thing I researched the first week of school is the EM drive, which is a drive created by a British scientist that can run in zero gravity without propellant. The second thing I researched is a blended wing, which is a new plane design that would greatly increase fuel efficiency, and drones, which are very useful tools that can assist in camera operations as well as others. So a little more in depth on the EM drive. It produces minuscule amounts of energy because of the scale of the object and the developmental phase that the product's in. So the EM drive works by bouncing an electromagnetic wave off of each end of the drive. And what happens is as the momentum changes, as it approaches and moves away from a magnet, varies the amount of force that it hits the wall with. So it consistently hits the side closer to the magnet with more force, which moves the EM drive in that direction. And this could be used in space travel, where weight is frowned upon, since it costs way more money to move weight into space, way more energy. And so what you want for long distance space travel is something that doesn't require propellant, so you can move at long distances as long as you have electricity, which is what this EM drive accomplishes and is very promising for the future. Second thing I researched was the X-48, which, as I said, increases fuel efficiency in the aircraft. And what the X-48 does is it takes a barrel out of the wing, and so you have all your cargo, your passengers, your pilots in the actual wing of the aircraft. And so what this blended wing design does is it increases efficiency and will allow these planes to travel for much farther distances on much less gas. And this is being developed in partnership between Boeing and NASA. The third thing I researched this year are drones. And the specific thing I researched about drones are the Australian firefighters who began to use them for UAV purposes and help them in fire rescue logistics. They used the UAV to get smoke analysis and found the safest routes to rescue victims from outdoor fires, such as from those produced from car accidents or forest fires. This also directly inspired my final product for the year that I'm working on, which is the firefighting drone that I will produce that can fly indoors in offices and house fires and locate people still trapped inside and help firefighters find them. So as I already explained, this is just a sample of what my drone is going to look like, and it's going to be able to assist firefighters in their attempts to rescue people. So I have some blueprints for my drone, and the components of the drone are like the engines, the wings, the camera, the fire extinguisher, the batteries, the flight controller, and all of that, so that the drone can fly indoors on 4 different rotors, which will give it enough propellant to stay afloat while it has a heavy weight of the fire extinguisher. And what the flight controller actually does is it recalculates what power to give each engine, much like an all-wheel drive car, so that it stays balanced in the air. This is a side view of the drone, where the fire extinguisher takes up most of the portion and the wings and engine are on a level in the center, so that the center of gravity remains somewhere in the middle of the fire extinguisher. Also, I have a front view, which shows another view of what the drone is going to look like, with the camera down there, the engines on the side, and the fire extinguisher in the center. And the actual size of the drone is going to be a little bit less than the width of that door right there. and about 6 inches tall, to a foot depending on whether or not I can create a heat shield for it. So the process I went through in designing my original work, which were the blueprints for the drone, is I hand sketched full-size drawings of the drone, which were about the size of that door. And I did that by taping multiple pieces of paper together so that I could draw the entire drone. And then what I did is I scanned sketches into my computer using the Genius Scan app on my phone. And then I digitized the scanned blueprints using Photoshop, making the lines and dimensions more clear, as well as listing out the components in an easy-to-read manner. So one day, I hope to inspire someone, myself, to do something great through my work, much like the astronauts in 1969. I hope to do something very successful this year in ISM, which is producing my final product of my drone. That's all.